Okay, so let's start and welcome to the conference, everyone. Happy to be here again, and I'm happy to see people joining another PTP session this year. So this year we will talk about the APIs that actually are used inside the Linux kernel that are connected somehow to time synchronization. We will start with a short overview of what pieces do we have in the kernel that are connected to it. Then we will talk about the Netdev IOCTLs that controls timestamping and enables the whole functionality of timestamping inside the network devices. Then we will introduce POSIX clocks APIs that are used for accessing the PTP clock using standard POSIX APIs. Then we will talk about the extended I/O calls that can be driven through this POSIX APIs and are specific to the PTP hardware clocks. And then tell a couple words about the transmit timestamping, how it works, because that's the most complicated part to get right. And then about receive timestamp. So let's get started. This is the block diagram of the overview of what components are there inside the kernel. So in the user space, we run our tools. Usually it will be the PTP4L from the Linux PTP suite. We'll talk to the networking stack to enable timestamping in the hardware and also get the capabilities of the device, then receive the timestamps along with the packet. And on the other hand, we have the PTP clock class driver, which is a translation layer because between our PTP clock driver that's specific to our hardware and the POSIX clock API that we will introduce a bit later. So basically the data comes into queues, goes through the NIC driver, gets timestamps obviously in the hardware from the PTP clock that's inside the hardware. So this needs to be exactly the same counter as the PTP clock is. Then the packets will come in, get timestamped, will be passed to the NIC driver and to the networking stack, and along with the packets, we will get our timestamps for receive path, and for the transmit path, it's a bit more complex, but I'll talk about it. So let's start with the control and info path. So how can we actually understand what our device supports, how it goes? So there is an ISTOL IO called get the timestamp info. This one will return the index of the hardware clock that's assigned to our net device. And will also inform the user space about the capabilities of the device. So the TX mode, which mode, such as two-step timestamping or one-step timestamping, the device support, and the support as receive filters. As you may not want to timestamp all the packets that come in, and you may have the hardware that is capable of actually understanding what packets are you sending and then just timestamping the relevant ones. And it's used, that's an important piece, it's used by the PTP4L to actually resolve the Netdev to PHC connection. So if you just give the interface name to the PTP4L, it will then call this IO call to actually understand which PHC is attached to this device and which device under the PTP it needs to actually talk. So the other piece is the Ethernet specific IO calls. Those are used to, this is the SIO get hardware timestamps, which gets the actual configuration of the timestamping. There will be a slide that will talk what configuration is there in a minute. And there is another IO call that actually sets this configuration. And this is important that there is the important part is that there is no API that actually gives us the capabilities, so we still need to get back to the ISTOL IO call to get the capabilities. So this only gives us the configuration, that is actually on the device. So to actually support those IO calls, there are two function pointers in the Netdev structure that were introduced in the kernel 6.6 that takes care of that are easier to implement, because in the past there was a generic IO call that you need to implement fully the copying of the buffer back and forth and resolving which IO call you actually call. Now there is an easier way that actually is better and easier to implement. So there are those two function pointers that are called when the device receives the IO call. This wrapper handles copying the buffer data, so the configuration from the user space back and forth, because the set command also returns the configurations that it set, because it's allowed to set a different configuration that was requested if it's more generic and your hardware does not support this. So those are those two functions. And that's the legacy way, the fallback. So the kernel will still fall back to the generic NDO if IO call. This is the generic IO call that's called for different functionalities. But I haven't really seen anyone implementing anything but timestamping in it. I know that there are other functionalities allowed through this IO call. So the problem with this is, it requires manual handling of the buffer. So we need to copy it from the user and then back to the user. And this is one entry for both flags. So both get and set actually lands into the same IO call, and you need to resolve it there, and you need to generate more calls for the same functionality. So the whole configuration is conveyed in the hardware timestamp config structure. The kernel version is a bit more rich because it also has the flags for copying it back and forth. But generally, it contains the information of the type of transmit that your device supports. So you can enable the two-step or one-step timestamping, and obviously disable timestamping at all. Important that when the device comes up, the timestamping is always off. So you need to turn it on to get the functionality. And on the receive path, you can filter out the packets, as I said just a minute ago. And the important part is, if your device does not support the flags that the user requested, you can fall back to timestamping everything, and it's right, but you need to get it back in the return of the set IO call. Yeah. So we can go along. You mean like if you enable the timestamping? Yeah, as far as I recall, the TSO disables timestamping. It's mutually exclusive, and you cannot really timestamp TSO packets. What I recall from most of the devices that I worked on. Yeah, but you usually don't. I mean, for PTP, you don't do it. But yeah, I understand there may be new functionalities that we want to maybe add that functionality. So yeah, that's a good topic for actually how to expand and what's missing in there. Because it's not defined in any standards which bucket to timestamp if you get such packets. So that's the structure. It also has some sharding functionalities. So there is a flag that it was copied to user, and the whole pointer to the whole request for the IO call. The user space doesn't have it, and it ends just after the RX user. So it accepts the flags, the TX type, and the RX user. Okay, so now let's talk about the POSIX clocks API. So this is the API that user will use to control the clock, and how the command from user translates into the API that's actually on the driver side. So the PTP clocks conform to POSIX clock standard. There is a layer that translates the POSIX clock calls into the APIs of the driver. So there is a clock adjust time that adjusts the clock. The fun part is that this is actually not a part of the IEEE POSIX standard. So this is the POSIX standard of Linux, and actually this is kind of do all function for controlling the clock, because it actually has 3 different functionalities depending on the flags. There is a clock get time, which gets the time, obviously. And there is a clock set time, which sets the time of the clock inside your device. And there are a lot of IO calls, which we will talk about. It will not be very great, because there is a lot of them and there is a lot to cover. So brace yourself. Yes. Mm-hmm. Yeah, the exposure is done by the class driver. We need to implement the functionality, but I will list them all as we go along. And you need to fill in the structure and then register the clock, and that will magically appear in FPT. But yeah, I will cover that all. So yeah, the PTP clocks are exposed as character drivers in the dev as PTP X, where X is the number of the given clock. The file can be opened by a process, obviously, and file descriptor with those magical macros can be converted into clock IDs. Because if you want to use the POSIX APIs, so the clock get time, clock set time, clock adjust time, you need to work on the clock ID. So we need to implement this macro in your code so that you create the file descriptor that you get from opening the file into the ID of the clock that you pass into the APIs. So yeah, this is what you asked for. This is the mapping of the POSIX clock operations, and this is what our driver exposes in the PTP clock info. So your driver will actually need to implement all those functionalities. Well, not all of those, but the ones that are relevant and the ones that are not really legacy. So some of them have the fallback, but I'll talk along as we go along. And this talk will actually connect all the dots. So let's start with the clock adjust time. So this is our do everything function in the POSIX world. So depending on the flag, it will either adjust the frequency or adjust the offset, or there is a new functionality to set offset, which is on the surface similar to the previous one, but in the depth, it's actually designed to do something different, but we will get there. So as I said, clock adjust time is not really part of IEEE POSIX. It operates on this huge structure, and this structure will actually be, I will talk more about it on the talk tomorrow about new APIs, because the current version of the clock adjust time, the clock adjust time, if it's called without any flags, should return this structure and actually fill it in. But so far, the only thing it fills in is the resolution of the clock, which is covered in the clock precision, if I recall correctly. But generally, it doesn't really return too much. It's the current frequency also. So only this field from this big structure will be filled, but we obviously will want more, but this is the topic for tomorrow. We first need to get the understanding of what we have so far to actually build along on top of that. So when this function is called with the adjust fine, with the adjust frequency flag, then it will adjust the frequency of the hardware clock. So we need to change the clock, the rate at which your clock ticks to actually match whatever is passed in it. And if it's called with the adjust phase, this new functionality, then it will adjust the PHC by a given number of nanoseconds. But this function is the new API that's actually designed to feed that offset into your internal servo in your device. So it will not immediately step the clock just dumbly, but it should put it through a servo and actually on the device calculate the whatever correction is needed. There is like the old way, which is the adjust time. This is just a one that will step your clock forward or backward, whatever the user calls. And without flags, as I said, it will return the current clock state, so it will only return the frequency, the current frequency correction. So the next one is the clock get time. Clock get time will call either of those two functions. It will first try the new one, the get time x64. And if it doesn't, if your driver don't implement it, which should never happen on new devices, it will fall back to the get time, the old implementation. So the main functionality is obviously to get the current time of your device. It calls the get time x64 if it's implemented, which is the more feature-rich implementation, which will also cover reading the system time just before the read of the register, the last register of your clock. Because usually the clocks are 64 bits, we usually read them by 32 bytes pieces. So this functionality should read the system time just before the last register read of the clock, and then immediately after it. Why is that? We will come back to it. But this the same function can be called here, and then it will not return the system clock. It will just ignore the system clock and just get the value of your clock. And the legacy functionality is the get time, which is just returning the value of the clock without the whole system time reads as well, that are around the read of your clock. And the pro tip is that if you write some kind of applications, you should really never rely on the get time because our devices are somewhere behind the PCIe bus, which always causes some delays. So if you try to directly just get time of your clock, it will always be a stale timestamp from the past when you like ask the device to get you time. So the next one is the clock get rest function. This is not really calling into anything inside the clock info. It's terminated in the class driver, and it basically returns the resolution of the clock. The important part is that this is the resolution, not the tick rate. So it's not tied to what your clock ticks at. So because the devices usually have clocks that tick at 2 nanoseconds, 4 nanoseconds, something like that. So it's not this information, it's the resolution of the clock. So if your clock still returns a single nanosecond, it's still valid that it returns 1 nanosecond. So statically, it's just a function in the class driver that returns 1 nanosecond resolution. The next function is the set time. This is a function that sets the clock to the specific value. It checks as the also adjust functions will check if your clock is free running, because the kernel recently introduced virtual PTP clocks. So the way they work is they overlay a virtual clock on top of your physical clock over the kernel APIs that actually can get the cycle counter and time counters. And then your hardware clock needs to be free running, because if you change the time on your hardware clock, you will invalidate all the virtual clocks. Basically, they rely on this. So when it's not free running, it calls a set time 64, which should basically just set the time of your device. So now the very long part about where the IOCTLs go. There's plenty of functionality that is actually exposed through IOCTLs in the PTP subsystem. So IOCTLs allow advanced operations on PTP clock. It's what we want to call it, and why we want to implement so many of them. So they read the clock capabilities, or they control external timestamp sources. Think of it as an external signal that needs to align your clock. They control periodic outputs, so the other way around your clock will generate the PPS signal. They control PPS subsystem, which is always, well, not always, but was in the past confused with the external timestamp source, but it has a different meaning in the kernel. It controls hardware accelerated cross timestamps, so for example, a PTM. It captures the offset between the clock and the system time in 2 ways, and controls the auxiliary pin. And for all the IO calls, there are 2 versions of them. One version without the number 2, and one version with number 2 at the end of them. The versions with number 2 at the end will strictly check the arguments, so it will check if all the reserved fields were zeroed and all the flags were passed correctly. So the first function is the PTP clock get caps. It returns the PTP capabilities. So the capabilities are basically copied from what you initialized your clock with, along with checking whether some of the functions are actually supported by your device. So for example, that's for the cross timestamping and adjust phase. Those are the values that basically based on the implementation of your function. If you implement them, they will be true and so on. So this is a generic clock class driver function, so you don't need to implement it already there. You just need to fill in all the arguments, and then they will get returned. So the next one is the external timestamp request. You will see this function a lot. So this one controls external timestamp sources. So think of them as PPS input pin. So if you connect the GNSS receiver, for example, that generates 1 pulse per second signal, it will be covered by this request. The configuration of the input will be covered by this request. So this is the PPS input that actually reports PHC, so PTP hardware clock timestamps via PTP clock. So they will be fed into the queue that's attached to your clock, and we will be able to read those timestamps from the device. It verifies the request against number of external timestamp sources, value, argument, and calls into the enable function, which is a Swiss Army knife function that actually covers all the external signals. So the next one is the PTP periodic output request, which, as you can see, also goes into enable. So this function controls the external output. So when your device drives the PPS signal, this will be enabled by this function. It will verify the request against the number periodic outputs internally, and if it's valid, it will call out into enable function. So the next one, the PPS, as you can see, also calls. So this controls the PPS subsystem callback to the clock. It's not designed to do the sampling of your clock. It's designed to generate the signal into the kernel to the PPS subsystem to align the system clock to the time of your device. It's not the one that some people implemented this as the just regular PPS in, and it also goes into enable. So the next one is the sysoffset precise. This is our functionality that will be used if your device supports the hardware accelerated cross timestamping of the time of your device clock and the time of your system clock. So for example, PTM falls into this category. So if your device supports PTM, will need to implement this functionality and return the cross timestamps calculated based on the PTM transaction. So this one requires hardware support. It uses the cross timestamping, so this function will return try to capture the system and PHC clock, so your CPU clock and your clock of your device at the same time, hopefully atomically, but not always. Like transactions may be different, but generally it's the hardware way to capture both clocks at the same time. And that's what it actually returns. So it will return the measurement of the clocks. So it will get the device time, it will get the real time and the monotonic row timestamp that are hopefully captured at the same time. The next one is the system offset extended. So this is the new function that calls into get time x4. So this calls the get time 64. This requests the measurement of the offset between the two clocks. So like I said, it should read the system time, then read the last register of your clock, and then read the system time again, so that you have the both of them captured as close as possible. So the way that we can do a fallback if we don't have the hardware accelerated like PTM, then the way to do it is to capture those two timestamps before read and after read, and hopefully assume that the system that your clock time read happened exactly in between. We don't have better way. It never happens this way, so it always causes some offset to be there, but it's the best way we can come with unless we have some hardware support. And then it actually allows capturing multiple samples. So your driver, the important part is that you need to capture the system time in your driver inside this get time x64 function. And then the call will actually contain the number of samples from the user. So for example, PHC POSIX will, if I recall correctly, try to read this 10 times so that it contains 10 samples. Then it finds out which one was the closest. So the pre-time and post-time are the closest to each other, and use that sample as the best sample it captured to actually synchronize those systems, or rather measure the offset between the clocks. Okay, so another function is the sys offset. This is the legacy way of doing the same functionality. In this case, it's a simplified functionality, so your driver doesn't need to capture the system time inside. It reads the system time in the character device. So in the subsystem first reads the system time, then it calls into your driver, and when it gets back from the call, it measures the system time. It's the worst way because the offset between two captures will be much bigger. So this is mostly a legacy. You shouldn't really try to implement this legacy way. So only get the get time 64. Always try to implement the get time x. And it also can capture multiple samples, just like the other function. So the next function is the PTP pin get function. So this one will actually get the pin configuration for a given pin index. So we give it the whole pin subsystem is used for the devices that use the pins that can have multiple functions. So you, for example, have the input-output pins for your device, and you need to configure the direction before you enable them. So this function is used to actually get what you configured on the device. And there is a pin set function, which also have an additional call that's called the verify, which will check with your device if it's okay to assign a given function to the pin that the user tried to call and set the function to. So this, as I said, controls the advanced pin assignment, such as bidirectional pins or multi-purpose pins. It verifies the configuration and stores it in a local table that's handled by the class device. So we don't need to implement that. But there is a PTP find pin function that can retrieve. If you implement this magical do everything enable function, you can actually find which pin was assigned to it by using the PTP find pin. So if you need to reconfigure something in your device to enable this direction of pin, you can find which pin was assigned to your functionality that the enable function tries to. So now how the timestamps are really made and handled inside the kernel. So let's just quickly recap how the device, how the software can actually control the hardware time in your device. So the driver will first create the PTP clock info. It will fill in the arguments such as PPS and per out, max adjust, the ones that were on the top of the table, and will implement all the functions and initialize function pointers. Potentially, it can query the hardware capabilities, obviously, then create this structure, and then it will register the clock using the PTP clock register. This will actually cause the subsystem to create this character device, and then you will be able to actually talk to your hardware clock. And the application can use the POSIX clock system calls, so all those clock get time, clock adjust time, and clock set time, along with the IO calls that we just discussed that can be sent to the same device, and then they will actually be passed down to your driver using the character device translation layer of the IO calls, those implementations that are actually done in the character device. So now the control path of transmit timestamps. The application first needs to send the IO call, the generic Ethernet IO call that actually sets the hardware timestamping. So this functionality will cause the NIC driver to configure timestamping in the hardware. So it will enable whatever is needed in your device to actually start timestamping, not for a given queue or something like that, but generally in your device. So it needs to enable, I don't know, pi timestamping if you support it or something along those lines. Then the application will create a socket that it will use to transmit the data, and using the socket options, it will enable timestamping for a given socket. So once then the packets that will arrive to the driver will have the SKB hardware timestamp flag set. In this case, you know that this packet requires special care, and you need to handle it in a special way so that you can return the timestamp once your device is done with your packet. So if you see this flag and you support the hardware timestamping, you need to modify the SKB that it came into with and set the SKB in progress flag inside this SKB. This will cause the stack to not immediately just get rid of the packet and call it a day and return the software timestamp that will be generated by your driver if you actually support it in the software. Because there is a fallback in software where you can generate the software timestamps in your driver. This will instead cause the stack to wait until you are done with the packet and you send it back to the application. We need to keep track of the original SKB, so you can't get rid of it because you will still need this SKB to return the timestamp to the right application, the right place through the stacks. So then when the NIC transmits the packet, it will actually generate the timestamp because obviously packet needs to get out for the timestamp to be generated. That's a chicken and egg problem. You can't get the timestamp from the packet. That's not sense. It doesn't make much sense. So once your device is done with sending the packet, it will send you the notification that, okay, I generated this timestamp. Now you driver take care of making sense out of it. So then you need to read the timestamp back, connect it to the right SKB that the packet was sent with. And the NIC driver needs to set the special structure for the hardware timestamp and set the hardware timestamp field to the timestamp that it's received from the hardware. But this timestamp needs to be converted to the time that the application see. It's not a raw timestamp if you don't support the clock that runs in the reasonable time scale. And you need to convert it to the time that's specific to this domain. And then you need to call the SKB tstamp tx and give it the original SKB. This way, the stack will know what to connect this timestamp to, and will inform the application using the error queue, and will send this timestamp to the application using the error queue. Are there any questions? Or yes. Mm-hmm. So you don't have hardware timestamping, but you do have a hardware clock. That's a tough one, because probably there is no way you can get better than software timestamping in this way, because you would need to, when you transmit the packet, you would need to read the hardware clock, but this will always give you a stale time. Mm-hmm. That would probably require a custom software, because it is, as I understand, it doesn't work on just regular packets. But the main question would be, can you send those packets somehow or trigger them from the user side? Because if you can trigger them, then you can write an application and use the same path to return those timestamps to the application. But it will not be a PTP4L. It will need to be a special custom piece of software. But it should be doable. Like, you should be able to get those timestamps. But you can get both, right? Transmit and receive. Because you need. Mm-hmm. Yeah, I understand. But it's important to get the timestamps from both ends. So if you can convey the timestamps on the access point, then you probably should be able to implement something based on those. Yes, the problem will be with yes, because this should technically work for the filters that you set. So if you recall the enablement, the IO call that you sent initially, it contains the filters for the receive packets. So the stack will technically expect the packets to be timestamped when it's set. Yes, but the thing is. Mm-hmm, mm-hmm.
So you can't really say even that I have a certain packet filter and these packets are going to get a timestamp, because those packets that are getting a timestamp are management packets that will never ever make it out to the Netdev, right? So it's kind of a separate path, and I'm just wondering if any thoughts on how could that be integrated? Could that be, or is it just bound to always be a complete separate stack in terms of application and everything?
It sounds like it doesn't really belong here if you can't send the timestamp. you may think of, for example, an implementation that will return the timestamps in the queue that's designed for the external source timestamping. So the one that's used for PPS signals, for example, and then write a custom software that will actually understand, try to figure out. But the biggest problem will be the path delay in this case, because especially in Wi-Fi, it's pretty hard to figure it out, right? Because
the Wi-Fi protocol has more times out the days, and the management packets have a whole bunch of timestamps when you started sending it, when you received it, when you got back, and so you can correlate those timestamps very well between. You have to do multiple exchanges, obviously, to like the previous packet's timestamp over in the next set. Then you can actually do the correlation that you need to do the synchronization.
That may be a good to come back to that tomorrow on the session about extending the PTP APIs.
Sure.
Because that may be a good segue to this talk, because I also want to talk there about the devices that are synchronized somewhere else.
Sure.
So this sounds like a case for that one.
Yeah, thanks.
Yep. Maybe pass the mic.
Yeah, so question. You said that basically need to disable segmentation upload when on stamping, and also you need alt SKB for like quite a bit. So I wonder, you basically kill your network performance with this feature, and I'm curious how
If you would like to timestamp all the packets, then definitely yes.
Okay, so what is the use case?
What is the use case?
Yeah.
Basically, if you want to synchronize your clock, you have the IEEE 1588. Go back to past Netdev, I talked like a lot about it, but it defines the synchronization. Also, the next talk will just quickly introduce 1588 as well. So it's used for synchronizing the clock on your device. And once you have this common clock reference, you can do, like, there are many use cases that come after that. I talked more about the use cases on my past talk. We have some time. So, for example, if you have a common reference in your data center, you can start, for example, transmitting packets at a certain time. One of the use cases. The other is just having a common reference for your applications, so that you can synchronize your system time and have a common reference across your data center and do something based on time, which will mean that all your servers will actually do something on the common scale. Okay, so we still have receive timestamping left, unless there are other questions. Okay, we can take that. Receive is pretty simple, because the application needs to set the RX timestamping, obviously. Using the same IOCTL, the same set hardware timestamp IOCTL. Then the driver will set up the hardware to generate timestamps as the packet come along. But this includes those hardware filters that may actually generate those timestamps only for some packets, not for all. Then the application will set socket options to enable receiving hardware timestamps along with the messages. And the hardware then, as a result, will generate timestamps for the relevant packet. For most cases, all the packets that come into the given queue. It will notify the driver that the packet came in along with the timestamp. Then the driver will need the receive descriptor and the receive timestamp. Once it builds the SKB, it will need to set the hardware timestamp inside the SKB. There's a nice macro to actually get the relevant fields. And the application will be informed by the stack using the C message with that is basically when you receive the packets all together. And those are the useful links and refer to once you be brave enough to start implementing this stuff. But hopefully this talk will make it a bit easier to start and at least do some heads. So yeah, that's talk. Thank you, and let's open floor for questions.
Right. Doesn't seem like the APIs necessarily prohibit use of TSO and GRO. For example, if
API isn't, but your implementation usually was. I mean, if you know, yeah, like I said, there is nothing that governs which packet should you really timestamp. So that is first thing we should probably start with when covering, how we want to handle it. Because for now, most of the devices, if they see that the queue is set up for the TSO, they will just disable timestamping for this queue and report that, sorry, timestamping is not supported along with the TSO. The API, yeah, it isn't prohibitive. It doesn't mandate that, but it's a problem of the device that will, you will somehow need to understand what you are doing. And especially that there is a certain pattern that is usually recognized by the device. That is the point where you do the timestamp.
That's kind of where I was going. It's like a tunable that says, I want GRO, a hardware GRO. I want first packet times packet times middle. I want all three. Right? Get a sense of time in between first and last. And same with TSO. You could easily have kind of a tunable or a config that says, I want timestamps for the packet, so give me first and last. I know how long it took.
Yeah.
What do you use it for? How long does it take the device to transmit a large TSO packet? So if you think big TCP with a bytes of data, and you're generating a number of packets based on some TX schedule.
It's generally useful if you want to understand the performance of the data center. You can get it out of the hardware timestamps, and then you know, for example, how long the packet took from one side to another. Generally about like doing the same thing on both ends. So if you timestamp the first packet on both ends, you will still more or less know what's going on. But like I said, I haven't really seen a device that supports timestamping and TSO together.
And then I take it the POC is not available through the VDSO. What the system calls to read, you need to do clock get time for PTP POC system call. There's no VDSO mapping.
Yeah, I believe so. I mean, this goes through the POSIX APIs.
Yeah,
they are like
real time. You can get through the V.
Yeah. But that's only true for system, and so it's actually on both Intel. But those are special calls that are handled in the user space.
So I understand that this conference is obviously focused very specifically on Netdev. So IB is a little bit outside what this conversation should be. But I'm wondering, is there any lead-in for setting up PTP functionality for potentially data streams that are using Rocky or RDMA in general that might not have SK, that might not use SKB and everything like that?
Inside the Linux kernel, no. It requires attaching it to the SKB. If it comes to InfiniBand, we support the PTP on IP over IB in NVIDIA. So you can use that as the time synchronization for your devices.
Got it.
A bit limited at this time, but we are working on getting it better, because the main problem for InfiniBand is that there is no, like for the Ethernet, there is a well-defined way of where should you timestamp the packets. For InfiniBand, this doesn't exist. So it's something that we need to work on.
Got it. Makes sense. Thanks.
Okay, so I believe 10-minute break, or? Yeah. Just wait for a mic maybe, because so that the bridge also can hear you.
On the RX direction, it's kind of more straightforward, like you should see messages. So on the TX direction, it's kind of convoluted.
Yes.
So how do you also use?
It's unfortunately not possible because technically your application is done with the packets that you send. Because the way the send works is fire and forget. We just give the packet and basically forget about it mostly. So the device needs to transmit it, but obviously you won't get timestamp before it gets out of your device. So from the device perspective, your packet is gone and there is no path back. That's why you need to keep the SKB and you go back through the error key. Because you can't with this C message way is good for the receive because you get the packet immediately with the timestamp. For TX, there is no receive path. You cannot really. Because then it will confuse the app. It will receive some timestamp without SKB, or it will loop back the SKB. There is no good way of implementing it.
Back on the Mac one, you send the message on the C message like next one.
Yeah, but the thing is the app also needs to know what this timestamp was for, because it can send a lot of packets and tell the stack to timestamp all those packets. And the way it currently works is that it actually gets the SKB and can match it to the timestamp. That's why it's the error queue way. Okay, so thank you all and enjoy 5 minutes break.